Hello everyone. Today I will present our work CAGS, Confidence-Guided Multi-Scale Aggregation for Sparse-View High-Resolution 3D Gaussian Splatting. Our work studies a practical but often overlooked problem in Sparse-View. 3D Gaussian Splatting. When only a few input views are available, how does input resolution affect reconstruction quality? In Sparse-View 3DGS, we may only have 3 training views, as in common LLFF or DTU few-shot settings. Existing methods often use heavily downsampled images to suppress artifacts. This improves global stability and reduces floating Gaussians, but it also removes high-frequency details, so the final reconstruction becomes blurry. If we directly use high-resolution inputs, the model can see richer details, but sparse-view supervision is not strong enough to constrain optimization. Densification may create noisy Gaussians, causing ghosting, floaters, and overfitting to the training views. This leads to our key observation. Low-resolution and high-resolution Gaussian fields are complementary. Low-resolution fields provide stable global structure, while high-resolution fields provide fine details. Instead of choosing one resolution, we combine them in a coarse-to-fine framework. The main idea of CAGS is simple. Coarse fields stabilize, and fine fields recover detail. We first build a hierarchical multi-scale Gaussian pyramid. Input images are downsampled to multiple resolutions, and the camera intrinsics are scaled accordingly, so all Gaussian fields remain aligned in the same world coordinate system. We optimize from coarse to fine. Coarse scales establish reliable geometry, and finer scales recover local details under guidance. However, high-resolution Gaussians are not always reliable. To address this, we propose confidence-guided aggregation. For each fine-scale Gaussian, we find its nearest coarse-scale anchor. We then estimate its reliability using 3 cross-scale cues: spatial deviation, opacity gap, and scale gap. Intuitively, if a fine Gaussian stays close to its coarse anchor and has consistent opacity and scale, it is likely to represent real scene structure. If it drifts away or behaves inconsistently, it is more likely to be sparse-view noise. These cues are mapped into a confidence score and propagated through a cross-scale confidence chain. During rendering, reliable Gaussians keep strong visibility, while inconsistent Gaussians are smoothly down-weighted. This is fully differentiable and can be integrated into standard 3DGS optimization. We also introduce multi-scale regularization. We sample pseudo-views by interpolating cameras between nearby training views and enforce consistency across multi-scale renderings. This gives extra supervision without requiring ground truth images, helping the high-resolution output inherit stable geometry while preserving fine details. We evaluate CAGS on LLFF, DTU, MIP NERF 360, and Blender under sparse-view settings. Unlike prior work that mainly relies on downsampled inputs, we evaluate at original, half, and quarter resolutions to directly test high-resolution behavior. Quantitatively, TEGS achieves the best results across multiple datasets and metrics. On LFF at original resolution, it improves PSNR by 2.73 decibels over the strongest baseline. On MEF NERF 360 at original resolution, it brings a 1.6 decibels PSNR gain. LPIPS is also consistently lower, showing better perceptual quality. Qualitatively, CAGS produces sharper edges, more stable textures, and fewer floaters in challenging high-resolution regions. The method preserves fine visual detail without sacrificing geometric stability. TEGS is also plug-and-play. When added to Drop Gaussian, FSGS, and Core GS, it consistently improves performance on DTU, with around 1.5 to 1.7 decibels PSNR gains. This shows that CAGS is a general multi-scale paradigm, not a method tied to one specific backbone. Finally, ablation studies confirm that both components are necessary. Hierarchical aggregation removes noisy Gaussians and stabilizes the field, while multi-scale regularization refines local detail and reduces overfitting. Combining them gives the best reconstruction quality. To conclude, our contributions are threefold. First, we systematically study resolution as a key factor in sparse-view 3DGS. Second, we propose confidence-guided multi-scale aggregation to turn the resolution trade-off into a complementary advantage. Third, our method is plug-and-play and consistently improves existing 3DGS pipelines across multiple datasets. Thank you for watching. The key takeaway is CAGS turns resolution from a failure mode into a multi-scale prior.